Okay, good morning to everyone. And that was Monk Around the World, Thelonious Monk, John Coltrane. And it's quite a contrast to yesterday with Jimi Hendrix and Purple Haze. So one put you awake, one I'm told put you to sleep. So somewhere in between there may be serenity, doing statistics. At this point, we go ahead and enter formally into a new chapter. That's chapter 3. We have spent time looking at a descriptive analysis from the point of graphs. Remember, that includes pie charts, bar charts for what kind of data? What kind of data for bar charts and pie charts? What? Bivariate data would be representing the data with a line, and that would be a numerical relationship. We're talking about bar charts and pie charts. When you go ahead and you look at stat graphics and you click on describe, what did you go to? You didn't go to numerical. You went to categorical, right? Categories. So we're talking about not numbers. We're talking about sets that you belong to. So in this case, it was what continent was a country in. So again, if you have categorical data, it's non-numerical in that sense, non-quantitative. Then we're going to use a bar chart and a pie chart. Now, if you're talking about descriptive relative to numerical data, what would you be inclined to use descriptively with a graph? The histogram, right? Now, the histogram allows you to see how the distribution is shaped. A bar chart doesn't. Okay, you do not see bell-shaped curves with bar charts. And I've had some people in their write-ups in this lab that I graded and returned to you telling me that a bar chart had the advantage that you could determine the shape of the distribution of your data. No. That's numerical data we're talking about when you look for a curve. You aren't hunting for a curve with a bar chart. Okay? You're hunting for frequencies, yes, but you have no intent on establishing that categorical data is normally distributed. But we are interested in numerical data. So the histogram was one descriptive analysis. What's another one you could do? The stem plot, stem and leaf plot, and the box plot. Now, the stem and leaf plot and box plot accomplish different things. What do you accomplish with the stem plot? The shape of the distribution. If you turn a stem plot, rotate it 90 degrees. So if you start at the low and go down to the high, and then just rotate it 90 degrees, you have, in essence, a histogram. And you can control the number of intervals using powers of 2. What do you get from the box plot? That's important information, but what do you get there that's quickly picked up with a box plot? Okay, skewing and outliers, suspicious and extreme, but the skewing, otherwise the anomalies to a normal bell-shaped symmetric distribution. So the box plot gives you a very good view of the skewing by looking at the relative position of what 2 measures. I heard the mean and the median. X bar and X tilde. The mean marker, which is your plus sign, and your median line, which is right inside the box plot usually. Now there's some weird box plots we can get with some data where things don't work out quite as you expected with small sets of data. But nonetheless, relative position of mean and median, and then what else tells you about the skewing? The whisker. The longer whisker typically on the side of the skewing. Now, what gets in the way of making that an absolute if we do a complete box plot? Okay, what happens with the outliers? Sean's right on that. What happens with the outliers? You only go up to a data point that's below what? the upper or, okay, below the upper inner fence, above the lower inner fence. So you don't go to the fence, and so if you have a suspicious point with a box, and then another point out here that's extreme, your whisker doesn't go there. Now the simple box plot done in your text, the whisker goes out to your highest and to your lowest data point. Then your whiskers are pretty self-explanatory. So you have to be careful. When you have extremes, suspicious points, those are going to bias your data set in the analysis you do. The mean is sensitive to the outlier. The median isn't. I can take a high point that's in the 500s when we're looking at something like, let's say, somebody screws up a data entry, and it was supposed to be 4.9. They miss a decimal point on the data entry, and it comes out 479 in birth rates. Now, if you look at that value and happen to note that the decimal's not there, it's very clear that this is a data entry error, an extreme point, and you don't want it. Will the median be in any way affected by that value? No. The median is a middle value. It doesn't in any way reflect the high and the lows. Hence, the median is often used in the business area, particularly with real estate, housing prices, and so on. When they talk about the average price of a house, they are typically saying the median, because it's not sensitive to those extremely expensive houses out of sync with the rest of the neighborhood. The mean is sensitive, the median is not. That's what you need to keep in mind. Now, the range gives you a sense of that spread. Okay, so we have another numerical measure that we've included descriptively besides the mean and the median, and that is the range and the standard deviation. Now, I've tried to give a sense of the standard deviation through graphs. And that is what Chapter 3 is about. Looking at a bell-shaped curve. So if you would turn to page 65, you're going to see a very typical histogram with a bell-shaped curve imposed on the histogram. Okay? Now, depending on your background in intermediate algebra, I don't know how comfortable you are with all the areas. I tried to indicate to you that there is in the Student Study Guide a complete review of the important ideas out of algebra that I think you need to reference and briefly review. One of them is an exponential curve. Now, technically, when we talked about powers of 2, we have y equals 2 to the x, correct? That's exponential. Now, the base, 2, is not the usual base that you think about with an exponential function. Instead, you typically think of e, right? E to the x. So y equals e to the x. E is approximately what value? 2.81. Close. You got your calculator. Take it out, find E. You were close, Sean. What do you get? What? 2.71. It's off by a digit, but I mean it's an important digit that you're off by. It's 2.718 if you keep going, and then it's, keep in mind, like pi, E is not a rational number. It is irrational. We say it's transcendentally irrational. It's not the solution to an algebraic equation. So e to the first is what you would be trying to get, and that is 2.718 and so on. Those digits do not repeat, even though it seems like as you look at e and you look about the first 10 digits, it looks like you might be getting something that repeats. It does not. What do we use that function for? Y equals e to the x. What does it describe? This is just a question based on intermediate algebra, some of the applications you would have done there. Anybody? What do you try to describe with that function?
Isn't it like the natural, like, it can be used to describe the birth and death rate of how quickly like an animal population, it can grow quickly until it reaches its like food source.
Okay, what you didn't hear, or you did? Okay, good. The mic was up, so we picked up on that. Is it, okay, the question was, what do we use y equals e to the x for? And the response had to do with natural kinds of things such as the way populations grow, the way populations die, etc. And the answer is yes. Now we use a slightly different form of that is available at your local pharmacy, non-prescription. It's a shampoo. Do you know what I'm referencing? Green bottle in its original form. You just don't have a serious enough relationship to intermediate algebra, I can tell. Okay, let me do some advertising. Now, they don't put it on the bottle this way. Pert. Go to Long's, go to whatever, and you will find that shampoo. Now, this represents your original population, initial population. This is the rate of growth, and this is the time in years. So e to the RT, P e to the RT, is the form that you actually used in an intermediate algebra to predict population growth. And we oftentimes think of that in the biological sciences where you have cells partitioning, dividing, and you have things growing in a petri dish and so on. The world population grows exponentially over a period of time. And trying to find the appropriate equation for the world's population growth is something we could do. We modeled that growth. What else besides growth? Sean was referring to things the way sort of die. What do we talk about with this equation when things aren't growing, like population of the world, populations of cities, populations in biological areas?
The decay rates of like
3 Mile Island, Chernobyl. You have radiation. How long does it take for the radiation to dissipate so you can come back? We talk about half-lives. And so the RT becomes negative in decay, and the usual phrase is decay. So we talk about growth and decay with this. Well, my point being, that was supposed to be a chapter you studied in an intermediate algebra. And typically you were asked to do something in graphing of this nature, e to the x, and then you might have such things as e to the 2x, or e to the 3x, or you might have e to the minus x. Otherwise, when you're trying to ask students to graph without a graphing calculator, you encourage them to do some plotting of points. And so we have a problem set that's supposed to have more than 10, 15 problems, so you have to get creative. And so you do things such as this, and as I say, by putting some coefficient in front of x, it has some effect on the problem. If the text is a good text, and you have looked at transformations out of beginning algebra, case in point, name the curve. Okay, you only have 4 to choose from, so you had a 1 out of 4 chance. It is the parabola. Okay? The arch of the cable of a suspension bridge like the Golden Gate, a parabola. And you did a thing called completing the square in beginning algebra. Probably didn't do it with any joy. But you then rewrote something like this. What did that do? Otherwise, if I start with this, Let's see, do I want to stay there? No, I think what I will do is make that 11. Okay. What do you do to get this in this form? Can anybody tell me? I'm not trying to teach an algebra course, but it's very critical to what I want to do with the stat.
Don't you add and subtract 3? So you complete the square.
Okay, 3 is related to it, but I wouldn't do that first. You're close. I need a step before then.
You can move 11 to the other side and then to complete the square.
Okay, I could, but I could do one subtraction and be there. What do I want to subtract from both sides? Put your two ideas together. What do I want to subtract from both sides? And in one, that's why I rigged it. What would you subtract to make it the perfect square? We are connected. Very good. Welcome to Palomar. For those of you, we've been talking about the shampoo you buy in the store. It's called PERT. It is the form of an exponential function used for growth and decay. And now we're talking about the kinds of problem sets that you would see in an intermediate algebra. And then I've segued briefly into beginning algebra, looking at a parabola, talking about this, and trying to get somebody to answer the question, what do I add or subtract to both sides in one step that finishes it for me? $14 was not the number. 11 is not the number. I want to do it in one step. I could do 2 steps. You give me the 2-step. The text is 2-step, but you haven't given me the 1-step. What if I subtracted 2 from both sides? And I've got 2 people that I think may connect with me. Okay, now see what Brian has to say. Anyway, let's subtract 2 from both sides. Okay, so I have this. Doesn't that make you feel warm and fuzzy? A few warm and fuzzies? Y minus 2 equals, rewrite the right side as a perfect square. X minus 3. Bingo! Now see, if I'd subtracted 11 from both sides, then I would have had to add 9 to both sides, and you could have done it just in one step by subtracting 2. That was the argument. Now this is in the form I have up here. Now why did I do that? Why am I doing this? Why do we make you go through this in a beginning algebra? What are we trying to do? Okay, if I use this phrase, does that communicate? 1 or 2 nods. When I wrote this, this is considered a standard parabola. It goes through where? The origin. Its vertex is at the origin. It's the classic. And I can take this equation and by transformation get it in this form if what? My new axis for the vertical is equal to y minus 2, and my new axis for the horizontal is at, well, I rephrased that. I should have said horizontal and vertical. The new origin is at 3, 2. So I'm going to transform. This is called a transformation. Origin to the ordered pair HK when I have it in this form. So I'm telling you if, and I didn't think this would go this painfully. So this is a little bit longer than I intended. But if I just take a standard dimension here, and so this is my original x and my original y, then I am arguing that the new origin should be at 3, 2. So over 3 up 2. And if I go ahead and create a new origin there and a new coordinate system, then relative to this new coordinate system, where I might consider this big X and big Y, what am I going to be graphing? In essence, y equals x squared. So if this was going over 1, up 1, and over 1, up 1, so I have that symmetry, and I think of my parabola coming like this. This is in, and I blew that, trying to get it through the point I wanted. Okay, so this is my parabola. All I've said is that that parabola has been what? Moved over and up, and is replicated here, and this, and again, that has to open up better. So if I can get a new origin, I can sketch what I know is here, over here, and it's a quick way of graphing. And I can do that with any of the conic sections. The conic sections being the parabola, the ellipse, the hyperbola, the fourth one. I saved the easiest one for you.
Circle?
The circle. Conic sections, ice cream cones for breakfast. The sugar cone. Not the one at Columbia where they make it out of a waffle and it looks like an ellipse at the cross section. Take a standard sugar cone, throw out the ice cream. Look at the top, you have a circle. Cut it at a slant and you have a parabola. Cut it vertically with the cone, with the two small points sticking together, and you have the hyperbola. Okay? If you cut it so that you still get, in this cone, something like this, then you get the oval or the ellipse. You can take any of those and put them in standard form. X squared plus y squared equals r squared. We're into intermediate algebra to an extent, although I do this in beginning algebra. That is the equation of a circle, radius r. Then you have x squared over a squared plus y squared over b squared equals 1, and that is an ellipse. Okay, and then you have x squared over a squared minus y squared over b squared, and that equals 1, and that is your what?
Hyperbola?
The hyperbola. And then, of course, you have y equals x squared, what we sometimes say is kx squared, which is your parabola. Now, these are the four conic sections that you're supposed to have studied in your 2 semesters of algebra, and then you talked about moving things around. So if I have an ellipse, well, let's just take a circle. How does its equation look? What are you trying to do like we did with the parabola? And that's where you have x minus h, quantity squared, plus y minus k, quantity squared, is equal to r squared. Now you have a circle with radius r centered at hk. None of that's new. So please understand, the last 5 minutes should not be difficult. It should just be a review. I should be nudging that nascent memory that is elusive to you at the moment. And so this should come back into your head later on today, driving down the street, looking for ellipses, hyperbolas, parabolas, and circles. What does that have to do with where I was trying to get you? And this is, as I say, taking a little bit longer than I wanted, but nonetheless, I'm trying to get to a certain point. Cameras, are we on 2? Okay, will you take one back to the left side, please, Jennifer, and show me the PERT, PERT equation, and what's below it. Now, I mentioned to you, typically, those first 2 equations, y equals e to the x and y equals e to the minus x, are given to you. And then sometimes you might be given this equation just to mix things up a little bit. E to the x squared. Okay, e to the x squared. Now, what does that do to your exponential curve? And by the way, we didn't really talk about what that curve looks like. So if I were to take a moment and just think in terms of y equals e to the x, let me do a couple of graphs here. This is the lazy man's way of doing two graphs simultaneously. Okay, give me a hand motion for what y equals e to the x looks like. That first one was a good log. Anybody else? Nobody could see what was... I see a hand starting to move. No conductors, nobody's into music. Okay, now a lot of you doing this. Well, you're thinking of half a parabola, but when you do that, you give me the log curve. Think of a jet plane taking off. It takes off with a rapid ascent. You're trying to go from Modesto to Stockton Airport. That's probably one of the most uneasy in the stomach takeoffs I've ever experienced. We had to take off from Modesto Airport and land in Stockton Airport. An immediate just up very fast and then immediately down very fast. It was like having that point of inflection unexplained because you're at plus or minus infinity kind of thing as we think of hyperbolas. But it's like the hyperbola squared. It goes through 0, 1, and you get this motion, and that's exponential growth. And the idea it starts slowly and then goes like crazy. The classic problem with powers at 2 is called Sess's reward. I pay you a penny the first day, 2 cents the next day, 4 cents the next day, 8 cents the next day. Would you work for me a month at that wage? And the naive says, for pennies, you're kidding. But try taking 2 to the 30th power and then divide by 100 and just see how rich you would be for that one day. That's where the problem came from originally, back in Greek times. Now, if you take e to the x squared, what is its impact on that function? This was y equals e to the x. So what happens as I take e to the x squared? How does it impact the curve? Steeper, right? So if x is 2, instead of having e to the second, you're e to the fourth. And so this thing still goes through 0, 1, but it's going to be what? Very close to 0 very quickly, and then do what? Much steeper incline. So if we have exponential growth at e to the x squared, things are getting out of hand real fast. Does e to the x squared do what I just did here? Now I got sloppy as I drew that. Is the left side going to drop down? E to the x squared. So I let x be minus 2. E to the x squared is e to the fourth, not e to the minus 4. So this thing does what? Doesn't come down here. It does what? This kind of thing. It looks a little bit like an extremely steep parabola. But it's not. Now, if the authors of textbooks in the intermediate level have ever had a course in statistics or taught stat, they give you this problem. Where am I going to put it? E to the minus x squared. Now, what is the impact? Without a graphing calculator, I know that you can do this in a graphing calculator, but it misses all the fun. Where's the high point on e to the minus x squared?
Negative 1, 0, or negative 0, 0, negative 1. You just reflect it across the...
You're close. Your answer is close. You said 0, negative 1. Try again. Okay, 0, negative 1, and 1, 0 are both very good wrong answers. Negative 1, 0 is also a very good wrong answer. You only have one combo left. Yes, Jennifer has it in the back, but we don't allow her to contribute. But I know she knows. Okay, Jennifer, I need to have you take camera 1 over here. I'm going to morph over to that side. We need to resolve this question because it's an important question. I will take straight edge with me, some chalk, and okay, the camera is going to stay where we have it. This is called modifying the lecture accordingly. Unintended consequence. Okay, let's come back to this. I'm having fun teaching algebra at the moment. Okay, so we said y equals e to the minus x squared. If x is 0, what is e to the minus 0? 1, not negative 1. Minus 0, 0. So we have, what is my ordered pair? 0, 1. I had 0, minus 1, 0, and 1, 0 all given to me. The only one that really I wanted was 0, 1. Okay, well, wait a minute now. Will y ever be negative?
No.
Now, I know the exponent is negative consistently. But is y ever negative? What is the impact of a negative exponent? So, for example, now we're back to pre-algebra. Well, maybe beginning algebra. If I tell you I have e to the minus 4, how am I supposed to interpret that? I do this, by the way, in Math 10, which is pre-algebra. What is it? Okay, it's 1 over the base to the positive exponent. And e to the 4th is most positive, because e is roughly 3. So that's 1 over 3 to the 4th roughly, which is 1 over 81, which is a little bit bigger than 1/100th. But it's a small number. Agreed? So what happens to this graph, roughly speaking? Okay, Jennifer, back to y equals e to the x squared on the right side. Yes, you got it. It's on the right side of the screen. What happens to that graph? Okay, I got two things happening simultaneously, and I'm going to put them together. One was this. It just turned it upside down, right? But then the point being, it can't just keep going down, because y would eventually be what? Negative, and we said y can't be negative. So if it's going down and can't go negative, what has to happen? It has to curve out. We have to have a point of inflection, which so happens to look like a what? Half a bell. And because it's x squared, there is symmetry with respect to the vertical axis. And again, I have said nothing beyond intermediate algebra. To wit, prerequisite for the course. And furthermore, in the student study guide, in the intro section, covering all the topics, including symmetry, transformations, and everything I'm talking about right now, is basically in that review. So you don't have to go out and buy a text. Just look at the student study guide, and it may shake some cobwebs loose. Now, I'm not doing a great job in symmetry there, so my apologies, but the camera is very forgiving. What do we say about the curve? We'd say it never touches, but it gets closer and closer, and so the correct word is asymptotic, like the hyperbola. We call that a density curve. And that's where I wanted to be 20 minutes ago. And it is the density curve related to, notice I said just related to, the normal curve, the bell-shaped curve that we've been trying to establish. Now we have some properties we want. The area under this curve. For those of you who have a background in calc, I'd be doing a definite integral from minus infinity to infinity, and I'd like that area to be 1 when I do the definite integral. And this is complicated by the fact that it isn't in a nice closed form in which you can look at a set of tables and just get the antiderivative. Essentially what I would want. I'd like that definite integral from minus infinity to infinity, and I'd like that to be 1, the area under the curve to be 1, and it isn't. And we have to typically do what we call a numerical approximation. We do a power series expansion using algebra, and then integrate term by term is what it's called. So with all that said, if you have no background in calculus, ignore the last 30 seconds. But it's not a trivial problem. I want this area to be 1 underneath that curve. And there is a very easy way of doing it. So instead of taking e to the minus x squared, we're going to consider this function. Because the area, and I have to do one more tweaking here, I'm not done, but the area under the curve that we're going to want, if I don't divide by that, would be the square root of 2 pi. So we divide by the square root of 2 pi. Still won't do what I want. Not moving the camera, and we're okay where we are. Remember this point right here had a name? What did I call it? A change of mind, change of attitude, change of, the correct phrase is curvature. Change of curvature. On each side we have that, correct? And between those 2 points, what did I say the other day? We have those points so that this actually has 68% of the area under the curve between those 2 values, and those 2 values are supposed to occur at where? The mean is the center, that's the Greek letter mu, and I'm going to add to that 1 standard deviation. So plus or minus 1 standard deviation, we want to give 68% of the area under the curve. Well, to accomplish that, okay, I can't use exactly this function. Okay? I have to divide it by something. A 2. So if I take e to the minus x squared over 2 over the square root of 2 pi, I have now as long as mu is equal to 0 and sigma is equal to 1, under that criterion, this will define the normal curve. We call this the density curve for a normal distribution. That's what we're trying to establish when we see the histogram. I'm going to leave that on the board for a moment. So Jennifer, you need to come back center on camera 1 if you would please, and I'm going to go back to the text momentarily, and we'll see where we are relative to the text. So I ask you to be on page 65. We're just going to turn the page. And we're going to turn the page a couple more pages. Let's see where I can finally, I'm hoping that at some point your text gives me what I'm hunting for as an equation, and at the moment I don't see other than, okay, we're on page 70, normal distributions, and what we have here is a statement, and I don't have that as focused as I'd like. There we go. Let's try that now, Jennifer. Okay, I'm on page now 70. And it says all normal distributions have the same overall shape. The exact density curve for a particular normal distribution is described by giving its mean mu and standard deviation sigma. Now, if we have what I said, standard deviation at 1 and mu at 0, we call it the standard normal distribution defined by the equation I have on the board. Let's go back to that. Now I mentioned to you finding the area for this, what's called definite integral, is something that is very demanding in calculus. And if I wanted to take the problem we just talked about, 68%, I just say standard deviation of -1 to 1, because it was centered at 0. 1 standard deviation to the right is +1. 1 standard deviation to the left is -1. So I would want this answer to this now. To be 0.68. That's what I want. So I should actually tweak this up here now. So it represents this. So this would now be over the square root of 2 pi. And this is over 2 here. And that is going to equal 1. One property of a density curve is the area under the density curve must be 1. Second property, the values of the density curve must be, otherwise y, must be greater than or equal to 0. And we're going to use that with a very simple example with a box called a uniform distribution in just a moment. But this is what we want to establish. And to do that would require an enormous amount of work if you didn't have a calculator or a computer. And in the days before computers, BC, before calculators, this was done with much difficulty. And so we created a very nice set of tables to do this for you. So if you will now, I'm going to have to go back to the front again. I'm going to leave this where I am. I'm going to hunt for this answer, okay, by going back, center, and I'm going to go a set of tables in your appendix, unfortunately. Not your appendix, the book's appendix, because you would have trouble extracting the information from your own appendix if you have one. We are going to be in the back of the book, and let's see if I can get far enough back that I can get to where I want there. How about 600? Now, if you're worried about finishing the course, we're at 684, so that should pretty well give you an idea we're going to finish. Here's Table A. Now, for the moment, I'm just going to go to I guess at the top there, I want you to understand that the table entry gives you the area under the curve to the left of the value. So to the left of -1, so I'm going to go over here now to the left side and hunt for -1, and it's right at the bottom of the screen. And to the left of -1, you see a 1587. Will you write that down? 0.1587. Now, without belaboring the point, 1587, just going to leave that there now. And come back to my curve here. And this may seem a little bit tedious and slow to you, but we're right now at the heart of the course in terms of what you're going to have to do. And you need to be feeling pretty darn comfortable with some of the things that are happening here using this table. So again, now I'm going to, not as good as I want, but let's go to the board. Remember, this is where the curvature changes. So I'm saying this was at -1. That's one standard deviation to the left. And this area here was what, 0.1587? Now, if there is symmetry, I should be able to come over here to that other point in which curvature changes. And if I draw my curve better, this line is not centered quite where I want, but it's darn close. Then what do you know here to the right of +1? By symmetry argument. 0.1587, agreed? The whole area is to be 1. So let's take 1 minus 2 times 0.1587. Would you do the arithmetic in your calculator, please? First, tell me the product of 2 times 1587. 3174, right? Which I hope maybe some of you can do without your calculator in your head. Okay, now subtract 0.3174 from 1. Number? 6826, and round off to the nearest hundredth for me, please. .68, yes? As a percent, 0.68 is? Move the decimal 2 places to the right. 68%. And what did we say? That between plus or minus 1 standard deviation, you should have 68%. Okay? We rounded off the value to the nearest hundredth. And we called it empirical rule? Empirical meaning from experiment, in essence. Okay, what was the other interval I gave you? Besides plus or minus 1 standard deviation? Plus or minus 2 standard deviations at 95%, right? Okay, new curve. Okay, I'm going to have to stack curves. Hate to do this, but since I don't erase anything during the presentation, I have to be careful how I manage the board, my time, and your life. Now, again, a poor representation of a bell, but we'll take it. Now, that's where the curvature changed. I modified the curve a little bit so its standard deviation isn't quite what the other one was. It's because my hand was lower on the board, and that's the best I can do. There's one standard deviation, so whatever that is, I'm going to simply replicate it out here. And here's my 2 standard deviations. To the left, there's 1, there's 2. So this is the region now for 2 standard deviations. So, referring to the table, what's the area to the left here of -2? Going back to table A, somebody just read me the number. I'll have to, well, yes, you can see it. That's fantastic. Thank you. It's 0.0228, yes? And by symmetry, what can you argue? Over here again, 0.0228, correct? And just like I did up here, I want 1 minus that, right? So I want 1 minus 2 times 0.0228. I guess that parentheses is unnecessary since I'm using an x for multiplication. Somebody give me this here. This is point what? 0.456, okay. 1 minus that, and what do we get? 0.954? Round off to the nearest percent. 95%. All right. Does it go without saying I can now play this same game with 3 and you would know how to do it, and you're not going to be surprised to get a 99.7? Rounding off the whole percent, we would have 100%, and so we want to realize there's something left in the tail, so we say 99.7. We got it? What was this predicated on? Let's slide over. Mu is 0 and sigma equals 1. Do you think every bell-shaped curve is going to be centered at 0 with a standard deviation of 1? No. Not going to happen. What could we do to take something centered at 70 and get it centered at 0? The answer has been given to you in that whole presentation on the front board. Front board time. Okay, right panel, right half of the panel, right above the ice cream cone. What would I do? I would transform the origin. Good, you win the trip to Hawaii? Hey, I'm not that wealthy. How about to ice cream store? So you can study conic sections. But we'll throw away we just say we want the cone. It's cheaper that way. And you don't need the ice cream anyway. So the weather's gotten colder. It was actually chilly this morning. See, some of you are in, well, 1 or 2 of you had coats on when you came in, right? We've gone from 105 to 70. It's like a ice storm. Now, what do you think I'm going to do to this equation if I want to center it at mu? Remember, h is going to be mu now. So what would I do to that equation? What? Not quite. What did I do, okay, at this point, Jennifer, to the left side of the front board? Where I have, yeah, that's fine, right there. How did I center this silly parabola at 3. What did I do? I subtracted 3 from x. Slide with me. I think the correct word is pan. Okay. So I slid over here, and now it's centered at 3. Do I have to worry about raising my curve? No, I want it where I want it. So k is 0. Now the sideboard. What am I going to do? This is plain dentistry today. I'm pulling teeth. What are you going to do to the x? Subtract? How many I want it to move. How far do I want it to move?
H.
Not h. It just had to be u. Mu. It just had to be mu. Okay, I'm going to write that over here because I don't want to mess this up. So slide with pan with me again, Jennifer. So I'm going to take y equals, I still have the square root of 2 pi here, but I'm going to modify this to e to the minus what? X minus mu, quantity squared, and I'll just put here in front minus 1/2. And now it's what? Centered at mu. Okay. Front board again, Jennifer. Over to, yeah, that's fine. Standard equation for this curve right here we said was y equals x squared, right? What if I give you y equals 3x squared? You'd have to divide by 3 to get it in standard form, right? Then it would be just y equals x squared. Okay, back to the sideboard. In order to get this transformed the way I want, so the standard deviation is 1, we divide by sigma there and sigma here. Finally, this will take any distribution that's normal, mu for its mean, sigma for its standard deviation, and it will modify it, transform it, change it to the following. So that it has a mean of 0, standard deviation of 1. And why would I like to do that? Because I can use table A to find the areas. Because, folks, not everything's between plus or minus 1 standard deviation. Not everything is between plus or minus 2 standard deviations. Maybe I only want to go 1/2 a standard deviation and I want the answer. I mentioned to you Chebyshev. Remember I said with Chebyshev it works for any distribution and the percent within that interval is greater than or equal to what? 1 minus 1 over k squared, where k is the number of standard deviations with the caveat. K must be greater than 1. Like a 1.5. 1 1/4. You don't have to have 1, 2, or 3 standard deviations. It's just a nice rule of thumb. Okay? So this is what we're trying to do. Well, this is starting to look complicated, right? So, in the spirit, yes, I have 1 minute for spirit talk. Let's go back to the front board. Remember I said we could rename this big Y and big X? And so I could have said this equation is big Y equals big X squared, and that's now in standard form, right? So we'd let big X equal little x minus h. So that's big X equals little x minus h. And some people get bothered because I have 2 x's there. So over the side, the last statement, I'm finally getting to where I wanted to be about a half hour ago. I'm going to let z equal x minus mu over sigma, and that's called a z-score. And so now I can, in the last 30 seconds, say that y is equal to e to the minus 1/2 z squared over sigma the square root of 2 pi, and that is what I wanted, with no time left. We're going to find z-scores. Now, back to the table. Do you notice at the top of the table? It said Z. I realize it's not in focus. See that Z? That's what we're talking about. Okay, I didn't get to do any of the problems I wanted to do, but I've covered the presentation I wanted to give, modified considerably. For homework, read this chapter. It should start making sense. Try some of the problems. They might make sense. And we will continue with this effort. Tomorrow you have a lab to get done, and so I'm nearly out of time. Oh, I can't even pronounce that after.